Hello, my name is Dodowin. This is the Advanced AI Course Project presentation. The title of this paper is Test Offloading in Ad Server for Semantic Communication. This is the content of my paper, like introduction, motivation, and the related work session, and after that the main point, system model, and the proper formulation of this paper, and finally we propose the solution for this paper, and after that we conclude. At the introduction part, the shift from the traditional communication system to semantic communication introduced a fundamentally new approach to data transmission, like that emphasizing the meaning of the transmitted information over raw data accuracy. Multimodal tasks such as VQA, visual question answering, like the present unit computation and communication challenge, necessitating advanced strategy to manage computational resources and ensure timely task execution. Task offloading, which involves delegating the computationally intensive operation from user device to more capable ad server, has emerged as a key solution to this problem. Despite its potentially task offloading in semantic communication system introduce new challenges, including the need to preserve semantic relevance, optimize resource allocation, and adapt to dynamic network and computational conditions in real time. The reinforcement learning has gained prominence as an effective approach for tackling the dynamic nature of text offloading and enabling real-time adaptability to fluctuating conditions. The motivation is semantic communication system by focusing on semantic relevance, significantly reduce communication overheads while ensuring meaningful data transmission. However, even with semantic communication, optimization task offloading in dynamic ad environment remain a challenge due to varying network state, resource limitation, and latency constraints. The motivation for this work lies in addressing these challenges by leveraging Q-learning to optimize task offloading for multimodal semantic communication systems like VQA, thereby enhancing system efficiency, reducing latency, and minimizing energy consumption. The task offloading in ad computing system has been extensively studied, with many work exploring various strategies to optimize latency and energy efficiency. In the context of semantic communication, the works, as we cited in the paper, then have proposed text dependency framework, leveraging directed acyclic graph DAG to optimize interdependent task scheduling. This paper built on this foundation study by integrating Q-learning into a semantic text offloading framework, dynamically adapting to changing system state and optimizing task execution for multimodal scenario. At the system model, a semantic aware task offloading framework tailored for multimodal application, especially visual question answering VQA. The local execution phase include two dedicated modules. The first one is text semantic encoder, and the second one is the image semantic encoder, which transform raw text and image input into the complex semantic feature. The remote execution phase leverage the computational power of ad server to handle the offloaded text with semantic representation and goal information fusion to create a unified understanding of the text. By utilizing transformer-based architecture, the system ensures high accuracy and robust semantic processing. This collaborative approach between local and remote components reduces computational demand on user device, minimize bandwidth requirement, and also enhance the system availability to handle complex multimodal task efficiency. This figure 1 is visually demonstrates the system interaction between local and remote components and also highlighting the seamless integrating of semantic communication and task offloading to optimize performance in multimodal VQA scenario. As we can see in the figure 1, there are two semantic encoders. The first one is used for the text, and the second one is used for the image. For the image, we have to name the query image, and for the text, we have to name with the query text. If we execute it in the local, we don't need to go to the remote execution. If we didn't finish the execution at the local server or local time, we have to remote the text to the cloud or some other base, and we have to make some transformer encoder and decoder during the remote execution session, and we have to fusion again the encoder and decoder things into the one thing, and we have to get back and to download the query test, something like that. So the problem formulation session, the primary objective is to maximize the semantic relevance of process tasks while adhering to computational and time constraint. The objective function is defined as the maximization of the total semantic relevance for all tasks, considering both offload and locate processing, as we can see in this equation 1. And for each task I, the binary decision variable with the xi that determine the execution mode we have to offload or not offload, or maybe any other way is we have to execute in the log or something like that. So in this case, the xi1 is indicate the task is offloaded to the S server, and xi0 value is indicated local processing. The constraint ensure practically applicable, including the first one is server capacity, is we can see in this equation 2, and the second one is semantic relevance threshold, we can see in the equation 3. And the final one is the time deadline for both offloading and local processing tasks with this equation 4. So this formulation effectively balances computational efficiency and semantic relevance while accounting for real-world constraints such as server capacity, test deadline, and quality threshold. The proposed solution is the decision-making process is modeled by defining state that capture the dynamic condition of the system, that is including the computational load on both the S server and user device. They're categorized into 3 levels: low load, medium load, and also high load. The offloading decision is run as a binary action. The action 0 is where the task is processed locally on the user device, and the action 1 is where the task is offloaded to the S server. To optimize the decision-making process, and the epsilon greedy policy is incorporated into the Q-learning algorithm by balancing, exploring, and exploration to discover better strategy while leveraging learned knowledge. The reward function plays a central role in guiding the learning process by evaluating the outcome of action taken, assigning positive reward to efficient decision and negative reward to inefficient one. By iteratively updating the Q value for the state action pair, the improved Q-learning algorithm land an optimal policy that balances the trade-off between local processing and task offloading. The inclusion of the epsilon greedy policy and the smooth learning curve visualization enhance the algorithm interpretability and stability that demonstrating it converges to optimal task allocating strategy. This adaptive framework provides a robust and computationally efficient strategy for optimization task offloading in semantic communication system while preserving semantic relevance and ensuring system efficiency. This figure 2 illustrates the cumulative reward over episodes, highlighting the conversion of the Q-learning toward algorithm toward an optimal offloading policy and validating its effectiveness in dynamic adaptive task allocating scenario. Finally, at the conclusion, by leveraging reinforcement learning, that especially an improved Q-learning algorithm with the epsilon greedy policy, we develop a framework that dynamically optimizes task allocating based on system state. The framework effectively addresses several key challenges in task offloading, including the trade-off between local and remote execution, that is maintaining the semantic relevance and optimizing resource utilization. The small cumulative reward provides clear evidence of the algorithm stability and convergence that highlighting the effective for the learning process. The simulation results demonstrate significant improvement in semantic relevant task processing efficiency and computational resource allocation compared to existing methods, validating the predicability and adaptability that proposed framework. This work represents an important step toward advanced semantic-aware task offloading strategy, and that is paving the way for more efficient and intelligent communication system. Thank you. This is the end of my presentation.